Hello there, this is Truth Socrates. Welcome to video number 35 for my series on multivariable calculus, known as Math 5C at Pasadena City College. So today's a big day. We're going to start a new chapter. So I will see you at the beginning of chapter 6 on page 305. All right, so this chapter is about the main theorems of vector calculus. And if you may have noticed, at the beginning of each chapter, kind of go through a list of what we expect to learn in that chapter. But I start out that description for this chapter a little bit differently because we're basically going to make connections between the integrals that we've seen so far. Okay, so in particular, we're going to look at three important theorems. These are what you might call the core theorems of vector calculus. So first we have Green's theorem, and this connects a contour integral along a boundary curve of a domain on the xy plane and a double integral on that domain. Okay, so two things will be going on here. We have a domain, that's our D, and we have the boundary of that domain. That's a curve. Okay, there's a connection between a certain contour integral along that curve and a certain double integral on that domain. And this is what we're going to do today in this video where we talk about Green's theorem. Okay, so down the road, we are going to see two more theorems, and they look a little bit like Green's theorem, actually. And we're going to show that if you squint your eyes a little bit, yeah, they kind of look like the same theorem. Okay, so Stokes' theorem connects a contour integral along the boundary curve of an orientable surface and a double integral on that surface. Okay, so it's a little bit like Green's theorem. You got a contour integral and a double integral. Now, the divergence theorem is still connected to Green's theorem, but looks very different from Stokes' theorem. And it's due by Gauss, and hopefully you recognize that name. He is one of the most important mathematicians of all time. So Gauss's theorem connects the surface integral, a certain kind of surface integral, to a triple integral along that solid. Okay, so these three theorems comprise the most important theorems in vector calculus. Okay, so to connect these integrals, we are also going to learn about the del operator, which we saw when we found the gradient of vector function of a scalar function, actually, and we will apply that operator to vector fields to produce other vector fields and other scalar functions. Okay, just to be vague about it. Okay, we're going to see more about partial derivatives. We're going to take second partial order derivatives. Ooh, kind of like in basic calculus, where we take the second derivative of an ordinary function to get the acceleration. Okay, so this operator we're going to apply to vector fields to get what are called the divergence and the curl of that vector field. Okay, so there are some interesting diagrams that we're going to see later on in this chapter. All right, so back in chapter 3, we introduced the double integral by reviewing the fundamental theorem of calculus. And then when we looked at contour integrals, we saw that the fundamental theorem for contour integrals is related, kind of, a little bit, to the fundamental theorem of calculus. So we compute, essentially, a contour integral not by directly plugging in the parameterizations and then finding a derivative, taking a dot product, and so on, but instead we look for a potential function if that vector field happens to be a conservative vector field. And then all we have to do is plug in the endpoints. Okay, plug in B, plug in A, subtract, voila, you get the value of the contour integral. Okay, unfortunately, that only works when your vector field is conservative. Okay, so fortunately, Green's theorem is a little bit more flexible than that. Okay, except we're going to be a little bit particular about what our curve looks like. It's the domain that is really more sensitive. Okay, so there's a laundry list over here. 4 properties that our curve is going to have to satisfy to fulfill or to apply Green's theorem. Okay, so it has to be piecewise smooth. Okay, so remember what smooth means. The derivative must always exist and never be the zero vector. So C is piecewise smooth if we can express it as a finite union of smooth curves. Okay, so maybe there are points where you have to attach one curve to another. Okay, so there may be 3, 4 corners, but as long as there's only a finite number of points where the derivative does not exist or is zero, then you're fine. You're piecewise smooth. Okay. The curve has to be closed. Okay. So what does closed mean? Okay, let me scoot up here. Closed means that the starting point, R of A, is the same as the finishing point, R of B. You start and end at the same point. Okay. Simplest example, you go full circle. Okay, so C has to be simple. Okay, so what does simple mean? It's a one-to-one function. So in other words, if you input 2 values for t and you get the same point, then you didn't input 2 different values. They had to be the same. Okay, so this has to happen except possibly at the endpoints. Okay, because we're requiring our curve to be closed, you have to start and end at the same point. So this condition does not apply to the endpoints, okay? But otherwise you can't cross yourself, so you can't do this, okay? So if you go back to a point where you already were, then you're not a simple curve, okay? The last condition is probably the most mysterious one. It has to be positively oriented, okay? So, what does it mean? Well, if we put the first 3 conditions, piecewise smooth, close, you start and end at the same point, and you don't cross over a point that you already went to, okay? So you can't do that, okay? But you have to start and end where you finish. So you can do this, and then back where you started, okay? So, or you can do this, and then back where you started. Okay. So what does positively oriented mean? Well, because you have satisfied the first 3 conditions, you basically have to go through your curve in an approximately counterclockwise manner or a clockwise manner. Okay? So positively oriented basically says that you have to go through a curve in a counterclockwise manner. Okay, so here's a parabola, y equals x squared, and we're only going from the origin to 2, 4. Okay, follow it by the line segment from 2, 4 to 0, 4, and then follow it by the line segment from 0, 4 back to 0, 0. Okay, so each segment is smooth, and you start and end at the same point, so you are closed, and you don't go through the same point twice. Okay, so the corners here, you only go through them once. Okay, so imagine that you have this curve, and you kind of just stretch it out into a circle. Okay, so a process that topologists like to call a homeomorphism. Ooh. Okay, so if you more or less follow those arrows over here, you are going in a counterclockwise manner. Okay, so that is a positively, so this is a positively oriented closed curve. Simple, closed, piecewise smooth curve. Okay, so if you go the other way, if you go to from the origin to 0, 4, and then from 0, 4 to 2, 4, and then from 2, 4 back to the origin, then that is a negative orientation. So here is Green's theorem, but I want to point out that we have a symbol here that we haven't exactly seen. Okay, So yeah, it's just a stylized version of the usual contour integral. But because we want to emphasize that we're going a counterclockwise way, we draw this circle around the integral. Okay, and truth be known, okay, can you tell if that circle is clockwise or counterclockwise? No, not really. Okay, on the whiteboard or the blackboard, we usually write it as a circle, and then we put an arrow, okay, to show that it is counterclockwise. Okay, if you don't put that arrow, nobody cares. All right, so what is Green's theorem? Suppose that C is a piecewise smooth, simple, closed, positively oriented curve on the xy plane, and D is the region bounded by C. Another way to say it is D is the region which is inside C. And it also concludes the boundary curve, of course. So suppose that F is a two-dimensional vector field. So the components are P of xy and Q of xy. And P and Q have continuous partial derivatives on an open region that contains the curve C and the interior D. Okay? So in other words, okay, you see the curve, you see the domain inside, just make it a little bit bigger, and you want your vector field to be continuous on that slightly bigger region. Okay? So of course that's not an issue if your vector field is defined over the entire plane. Okay? All right, so what does Green's theorem say? The contour integral of our vector field dr, our usual notation, going in the counterclockwise orientation, which we can write, of course, as p dx plus q dy, is exactly the same as a double integral. Okay, very surprising. How can a contour integral be the same as a double integral? Okay, but they are. And we will prove this, or at least one instance of this, at the end of this video. Okay, it's a double integral. What are we integrating? You take the partial of q with respect to x, the partial of p with respect to y, and then you subtract. Form qx minus py, that is a scalar function. Take the double integral of that scalar function through the domain D. Okay, so let me walk you through this example. Okay, here's all right, so here we are in our workroom, and let us do this example. Let me hide these. There you go. That looks a lot cleaner. Okay, so we have a curve made of the line segment from -2 to 4a. And then we want to follow the portion of this parabola, y equals 1/2 x squared, from 4/8 back to -2, 2. Okay, so we're going to go to GeoGebra in a minute and see just exactly what this is supposed to look like. But we want to use Green's theorem to find the contour integral of this vector field, okay, in the counterclockwise orientation. Okay. Oh, I'm sorry. My bad. Let me fix that, because let me just write it this way, the old way. Okay. So, and that's because, okay, do we know if this curve is positively or negatively oriented? Okay. Green's theorem is valid only if it's positively oriented. Okay, so what if it were negatively oriented? Well, good news. All you have to do is reverse the sign. Okay, so get the answer using a positive orientation, and then just change the sign of that answer. Okay, so before we go to GeoGebra though, let's see if finding qx minus py is going to give us something simpler or just as horrific as this ugly looking thing. Okay, so remember that the first component is our p, so p is this, and the second component is our q. Okay, so there we are. Okay, so we want qx. Okay, so find the partial derivative of q with respect to x. Y goes away. Partial with respect to x, that produces a y. Partial with respect to x minus 10x, and partial with respect to x minus 4. Okay, so qx looks simpler than what we are looking at right now. Okay, so how about py? Qx minus py. So p is over here. So yeah, why don't we move it down so that we are not so confused. So what does py look like? 0, 7x, 12y, and 2. Okay, so that is our py. Check 1 7x, yes, 12y. Okay, very good. So we want qx minus py. Okay, so let's take qx over here, and we will subtract py. And don't forget to put parentheses, or that will mess you up. Qx minus py. Okay, so you'll get minus 17x, looks like it, minus 11y, and then minus 6. Is that right? Yeah, I got it right for a change. Okay, excellent. So that is what we are going to double integrate over the domain. What domain? First, we have to draw a picture. Okay, so what exactly does this curve look like? Okay, so we need the segment from -2 to 2 for 8. Okay, there we go. And we want the portion of the parabola 1/2 x squared. So here's x squared over 2. Aha! There we go. We want to follow 1/2 x squared from 4, 8 back to -2, 2. Okay? So if you want a nice looking diagram, you would use curve. Okay? But please. So we want to go from here to here and back where we came from. Okay. So does that feel counterclockwise or clockwise to you? We're going around in circles, sort of, and we're doing it in a clockwise manner. Okay, so Green's theorem does not apply directly, but big deal. Okay, we will apply it directly to the opposite curve. Okay, so what is the opposite curve? We will go from -2, 2 to 4, 8 in a counterclockwise manner, and from 4, 8 back to -2, 2. So that is the same curve, but in a positive orientation. Okay, so after we apply Green's theorem, the contour integral that we want is simply the negative of that answer. Okay, so no big deal. Okay, so now we are back to chapter 2, okay, when we did the double integral. So is this a type 1 or a type 2 region? Well, if you shoot vertical lines, you enter at the parabola and you exit at the line segment. Okay, is it good to do horizontal? Yeah, I don't think so. Okay, we will have to split it into 2 integrals. Okay, so type 1 it is. We're going to set up and compute that double integral. Okay, so here's a copy of the description of the curve. We're going to need the equation of the line connecting these 2 points. Okay, so what is our slope? We want 8 minus 2 over 4 minus 2 plus 2. Ooh, 6 over 6, that looks like 1 to me. Okay, so the equation is simply y equals 1x. And then do we have a plus b? Well, to get from 4 to 8, you have to add 4. Okay, so yes, -2 plus 4 is also plus 2. Okay, so that is the equation of the line segment, our exit point. Okay, so the double integral that we want is, we said we'll set it up as a type 1. So left to right, we're going from negative 2, positive 4. Negative 2, 4, we're doing type 1. So the outer is the dx, and then our inner is our dy, of course. So for y, we are going from, okay, so remember the arrows enter at the parabola in the bottom. So we are entering at x squared over 2, and we are exiting at the line. Okay, so the line has this equation, y equals x plus 4. And we are integrating qx minus py. So we have this. Okay, and so this is not really all that bad. Okay, can you imagine? Just imagine if you had to parameterize the parabola. Well, it's not so bad, but plug it in here. Yeah, that's horrific. That's going to be horrific. Yeah, I'll see you in about 2 hours. Yeah, this is definitely a lot more efficient. Okay, and in fact, what's the final answer? Negative 5238 over 5. Okay, so the contour integral that we want, this, okay, is not this, but the negative of this answer. Okay, so that is our final answer because C is given the negative orientation, okay, in this problem. Okay, so to run around that, think about the opposite orientation, then we can apply Green's theorem, but the relationship between the negative orientation and the positive orientation is the corresponding contour integral is the negative of the other contour integral. Okay, so that's why we reverse the sign. Okay, and of course we know how to do the mechanics of this double integral. Okay, so integrate with respect to y. So you have an extra y there, you'll get a y squared over 2 and a minus 6y. And yes, there's still going to be some pain involved, okay, because you'll have to square this, you'll have to square that, you'll have to subtract. Then you're going to have to expand all that out. There's a price for everything, okay? So it's not like it's, you know, completely free, okay? There's still some work to be done. All right, so our first version of Green's theorems, we started out with a positively oriented, piecewise smooth, closed, simple curve, okay? Now, what's a way to produce such a curve? Well, one way to do it is to start with the domain, okay? So D will be a closed bounded region on the xy plane, and it's either a type 1 or a type 2 domain, okay? So in our example, that parabola with that, oh, and even the parabola with the line segment, those are type 1 or type 2 or both regions, okay? So you can join them together, except you're not allowed to produce holes. Okay, so that's the thing. You can't put together a triangle and another triangle and another triangle. Oh, except you could have a hole in the middle. Okay, so you're not allowed to do that. Okay. Yeah, and that's because the curve that we want is supposed to be continuous. Okay, because you know, the derivative has to exist everywhere. Okay, so if it's differentiable, it has to be continuous. Okay, if you have a hole, then your boundary is in 2 pieces. Okay, one way to think about that is take a circle and remove a circle. Doesn't even have to be in the middle. Okay, so now you have boundary on the outside, boundary on the inside. Ooh, they're not connected to each other. Okay, so that's not allowed. Okay, so we write C as the boundary of D. Okay, and yes, that's the del symbol as well. Okay, the other del symbol. Okay, so the rest is the same. Okay, so the contour integral around C of f dot dr is the double integral over D of qx minus py dA. Okay, so we mentioned that if you were given a curve which is negatively oriented, don't worry, just take the positive orientation, and then what you want is the negative of that answer. Okay, let me walk you through this example, which involves something that should look familiar. Ooh, polar coordinates. Okay, so here's a curve made of 3 parts. Okay, first is the line segment from 0, 0 to negative 3, 4. And then the portion of the circle from negative 3, 4 to 5, 0. And yes, that point is on the circle because you get 9 plus 16, it is 25. Okay? And then from 5, 0 back to the origin. Okay? Start and end at the same point. So it's closed. Each of these parts is smooth. So we have a piecewise smooth curve. And here we go. That looks again like a clockwise, negatively oriented curve because it's going clockwise. Okay, so yeah, if you do your qx minus py, okay, you get something simple, and you can easily do it in polar coordinates. Okay, so remember, x is r cosine theta, y is r sine theta. Okay, you have to know what your starting and ending angles are, so you start on the x-axis, so that's 0, and you stop at negative 3/4. So you can write that as an inverse cosine of negative 3/5. Okay, 3, 4, 5 triangle. We've seen that so many times before. Okay, so you know how to set up the double integral in polar coordinates. Okay, and after we have done all those horrific spherical and cylindrical integrals, yeah, this is almost child's play. Okay, so that is our final answer. All right, so we're going to end this video by giving a proof for a particular instance of Green's theorem. Okay, so Green's theorem is supposed to work for every kind of piecewise smooth, simple closed curve, blah, 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 okay? But can we draw all of them? Yeah, maybe not, okay? So here is an example where we can explicitly show that the contour integral and the double integral in Green's theorem are exactly the same, okay? Miracle. Okay, so we will look at a region which is simple, and by that we mean it is both a type 1 and a type 2, okay? So yeah, let's say we follow y equals f of x, and then from this corner, you form a horizontal line segment, and then from this corner, form a vertical line segment back where we started. Okay, so if we start at AC, all right, and our next stop is BD, okay, we will follow y equals f of x until we get to BD. We will go to the left until we get over the starting point of A, x equals A. So we're at AD, okay? And then we follow x equals A down back to AC, okay? So this, as you can see, this is a one-to-one function, okay? It passes the horizontal line test that we see in pre-calculus, that you should have seen also in basic calculus, okay, when we were doing exponentials and logarithms. Okay, so we want to prove that this contour integral is exactly the same as this double integral, okay? And what we're going to do is, it looks almost like witchcraft. We are going to separate the left and the right. Okay, so we're going to look at the contour integral of just p dx, and we're going to show by some miracle it's the double integral of the minus py dA. Okay, and similarly, the contour integral of q dy is the same as the double integral of qx dA. Okay, so it's almost like, wait a minute, does that always work? In this case, it actually does. Okay, and that's what makes the proof work. All right, so the first part of the curve is simple. You're on your f of x, okay? So r1 of t is just t comma f of t, and t is going from a to b, Okay, so that part's easy. Unfortunately, the second, we're going right to left. Okay, so that's not how we usually traverse a horizontal line segment. So what we're going to do is we'll do it the natural way, left to right, and that is at TD, remember y equals D, and T is going from A to B. Okay, but remember what happens if you reverse a curve. You only have to account for it by doing a subtraction instead of an addition. Aha, very clever. So similarly, the third line segment is going down. Okay, so we go up, x coordinate is always at A, y coordinate is T, T is going from C to D. Okay, so therefore the contour integral of P dx is these three contributions. Okay, now what is our dx though? Okay, so we have x is t, so dx is just dt. Our x here is also t, so our dx is dt. Oh, but wait a minute, our x is a, so dx is 0. Okay, so therefore the third integral does not contribute anything. Okay, and we have these two terms. Okay, so we're going to stop there for integral of p dx. Okay, so now we want the double integral. Okay, so let's go back to our domain, which is back here. Let's think of it now as a type 1 region. In fact, that's how it's set up over here. Okay, so x is going from A to B, and your y is going from f of x up to D. Okay, so let's set up our double integral. Okay, so we have minus py dA. X is going from, let me scoot down here. X is going from A to B, y from f of x to D. Okay, so dy inside, dx outside. However, we have a partial derivative with respect to y, and then we're integrating dy. Oh, so the partial derivative disappears. Yeah, the antiderivative is simply minus p of xy. Okay, so we go from f of x, y equals f of x, to y equals d. Okay, so we replace y with d for the first term, replace y with f of x for the second term. Okay, however, there's a minus sign there. Okay, so that minus sign stays there. Minus minus plus p of x, f of x. Okay, so the positive term looks more natural on the left, and then we have minus the one on the right. Okay, all right, so we have two integrals, and let's see, why don't we make it a little smaller? Yeah, that's a good idea. So check it out. We have this for the end of our left side of the equation, and we have this for the end of the right side of the equation. I guess I can make it a little bigger. Okay, so are these two really different? I see an f of t, f of x, td, xd. Okay, oh, wait a minute. If you just change all the x's to t's, or the t's to x's, you'll get the same thing. Okay, and remember, back in basic calculus, that's because we call them dummy variables. Okay, so the definite integral from a to b of f of x dx is exactly the same as the definite integral from a to b of f of t dt. It doesn't matter what letter you use. Okay, the final answer is a number. Okay, you will get exactly the same number no matter which letter of the alphabet you use for your variable name. So those two are exactly the same. Okay, so now we're going to do the integrals involving q. Okay, so this might look like the same diagram. Okay, and yeah, these are labeled the same way. Oh, except for this. Okay, so this time, okay, instead of y equals f of x, we're going to use the inverse function. So this will be x equals g of y. Okay, so we're going to keep the parametrizations for these two line segments, but now we have a different parametrization. Okay, so I enabled scrolling here. So this is the parameterization that we are going to use. Okay, so the parameter will now be the y coordinate, and the y coordinate goes from C up to D, okay, instead of A to B. Okay, and so x is g of y, so g of t. Okay, so this is our parameterization for the side of this domain. Okay, so we will keep R2 and R3. Okay, so we're going to look at our dy in a little bit. So y is t, so dy is just dt. Okay, R2 and R3, are they going to change? Here is R2, here's R3. Ooh, y is a constant here, so dy is going to be 0 for R2. dy is going to be dt for R3. Yay! So just like in our first pair for p's, one of the integrals is going to go away. Okay, so here we go. Okay, so dy is dt for R1 and R3, but for R2, dy is 0. Okay, so the contour integral for q dy is the integral along C1 for q of xy dy minus these two, but for the second one it's going to be 0, and this is for the third one. Okay, so now we treat this as a type 2 region, and that is why it was important that we have a simple region. It is now y is going from C to D, x is going from A to g of y. Aha. Okay, so this is our integral, double integral. Y going from C to D, dy on the outside, x going from A to g of y, q sub x, xy. Okay, but we have a partial of q with respect to x dx, so the antiderivative that we want is simply q of xy. Yay! We're going from x equals a up to x equals g of y. Okay, so plugging in g of y for x, we have q g of y. Plugging in a for x minus q ay, and we have this as our final answer. And are these two integrals the same as these two integrals? Yep, they're exactly the same. You just change your t to y, and you'll get exactly what we have over here. Okay, excellent. That is Green's theorem. And in our next section, we are going to do some preliminary work. We are going to learn about the divergence and the curl of a vector field. That will prepare us for the divergence theorem. Oh, big surprise, divergence theorem, but we don't call it the curl theorem. It has a proper name. We call it Stokes theorem. So until our next video, enjoy the rest of your day, and I will see you real soon. Bye-bye.